Why is someone pasting a monkey into the chat? Boy, high quality discussion today. Yeah, I only got like 4 hours of sleep or something stupid. It was not good. It was not good. What is up, people? All right. Okay. How do I like the culture in Singapore? Well, it's hard to say because I was only there for like 3 days. You need a longer term visit to know that kind of thing. Lock-free is neat, but what about weight-free? Well, one step at a time, man. I mean, geez. So I want to do a simple lock-free stack. And I want to do this one. This is from a paper in the 1980s, a relatively well-regarded, well-known paper that first talked about all these kinds of issues. The thing is, this is really hard to read because like I don't know this particular assembly language. I don't know what these order of arguments mean. So I want to try to search for maybe if somebody's written it in clearer pseudocode, because one little mistake in implementing this will result in a problem that may be hard to figure out. So I could start doing some searches. I can do like Schreiber free element chain pseudocode. The elements of pseudocode. No. Whoops. I don't want the elements of pseudocode. Why does Google search get worse all the time? Like, there was a time 10 years ago when I could do this search and I would find what I wanted. Like, what happened? Let's see if image search is any better. Like, how much better of a search am I supposed to compose here to look for what I want? Jesus. Must include. Oh, now it dequoted my free element chain. That's great. Let's see if this one has something. Stacks and queues. Michael Scott. Okay, it's just talking about these things. This is a survey paper that doesn't show any algorithms, which is fine. That has its use. It's not what I want right now. Oh, God. Okay, this is when you know you're not going to be happy, is when you start seeing these things. Oh, my God. Let's write our stack algorithm in denotational semantics. That way nobody will know what the hell it does. Oh, wait. It's almost more readable. Not quite. Okay, so do I try to translate this into real code? Or do I try to translate this into real code? I mean, I kind of prefer this. There was about 6 months in college when I thought denotational semantics was cool. And when I thought operational semantics was cool. Am I looking for Triber stack? Well, Triber stack would be fine. Like this is the Triber stack right here. It's just, you know, I don't exactly know what all these things mean exactly. So I'm a little, Like, I guess this is the data structure definition. This is the node. This is like the root of the list, and this is a list node. And I don't know what EQU star is. Does that just mean it's a jump target? Or does that actually do something? I don't think this is probably searchable. Oh, it is. I don't see any definition of that. I just see the word require and request. Who knew that so many words have EQU? All right. That's not the right one. It just looks like those are the branch targets. Triber stack Java example. Hopefully these guys didn't make a mistake. Let's see. Push new head, old head is top.get. So we get the old head, we set our next pointer, and we cast that onto top. Right? So let's compare that to this. Okay, so we get, I guess anchor P is what's called top here, right? So we're putting anchor P in R2. Okay, and this is setting the, I guess this was passed in as an argument. I don't know what this comma R4 is, but we're storing L, this is like saying L dot L next, I guess, right? I don't know what the comma R4 is. And then we compare and swap old head, new head, storing onto anchor P. And if that fails, go back, which is the same as looping. So I don't know what this R4 is. So is that like a secondary store? Are we also copying R2 to R4? And then the argument of this is old value. Wait. Old value, new value. See, I don't know. This R4 thing seems important, and I don't know what the hell that does. I don't think it's an offset because it doesn't get initialized anywhere. Although maybe R4 is guaranteed to be 0. I don't know. Okay, I get it. Okay, R4 is the input parameter. So here it says put R4 element on free chain. So what's going on here is the caller allocates a new element and puts the address of that element in R4. All right. So R4 is already initialized going into here. So this is saying R4 dot lnext, right? That's what that means. And then we're saying old value R2, new value R4, cast onto anchor P. Now it all makes sense. Now it all makes sense. I think EQU doesn't do anything. I don't know what that does. I don't actually know. Someone just linked a C++ version also. Let's drag that over here. Okay, the Java version definitely looks better. Jesus. I mean, what? Okay. Okay, so the pop, old head is top.get. If the stack is empty, return null. That's great. New head is old head.next. Okay. This is way more straightforward than I thought it would be. Are we sure this is right? Why am I trying to write a lock-free stack? Okay, well, first I just want to do some lock-free algorithms to test the intrinsics that we just did. But secondly, I actually have a use for it. I can show you guys. all the files, but so okay. So here, in the sound system, going way back in time, our sound system used to be one additional thread that would just run asynchronously to the main game. But trying to remember exactly what the series of decisions was. But basically, you know, we have sound effects that'll be like OGG compressed, for example, right? And if they are, decompressing that data is a little bit non-trivial. And if you want your main audio thread to have fast responsiveness, to like be done with every cycle relatively quickly, then you might want to farm this kind of work out to a secondary thread that, you know, opportunistically decompresses for some amount of time ahead of what you actually need, right? So that all those samples are ready. And you might even, if you're playing a whole lot of compressed sounds, want to spin up multiple of these threads. But I think we only do one right now. But so what happens is the main system has the compressed sound data, you know, in just a series of pages, and then we hand those pages off to a secondary thread to decompress them and to hand us back pages of decompressed data. And that's all fine. But we use just mutexes for that, which in Windows are just critical sections. And it's a very simple implementation. We just grab the mutex and put a thing in the array and then release the mutex, right? But that's just a little bit heavyweight compared to a lock-free queue, for example, right? A lock-free queue would be a nice thing to provide that would make a lot of people happy. But a lock-free stack is a little bit simpler than a lock-free queue, I believe. And so if we do the lock-free stack first, that'll be good. There's all sorts of other good things about it. So like this mutex implementation uses a Windows critical section, which is an operating system resource, which meant, you know, if you want 100,000 lock-free queues for whatever reason, you'd have to request 100,000 operating system resources, which is not great. Whereas if you do synchronization with compare and swap, you never talk to the operating system, and so forth. Is that Vorbis or Opus? It's Vorbis mostly. Actually, I think it's either right now. At one point in the witness engine, I supported both Vorbis and Opus, and then I think we ended up not using Opus because it wasn't good. But I may still have support. Let's go. Where is it? Cache decoder? I think we dropped Opus. Oh, wait. we have an Opus pre-skip, but I don't think we use it anymore. Yeah. Yeah. So if we want Opus support, I have to put it back. Do the Windows critical sections do the footex thing, or they avoid a syscall by using an atomic when there is no contention? I don't actually know. I think they probably do because they're supposed to be lightweight. But I believe that creating one is still a system call that takes a resource. I might be a little bit wrong about that. Because again, I don't, so whereas I've done parallel programming a fair amount once in a while, it's not the main thing that I do, and I have never done it in a very, very serious rad game tools level caring about performance way. And so usually if I do something, it'll be something like those, just a mutex with a queue and you pass stuff back and forth. And that's fine. But as I said in my rant in the last stream, that only really gets you a certain level of performance before it starts being a problem. I mean, it's fine for certain classes of jobs, that kind of thing is fine. But for certain classes of jobs, it's inappropriate. And to be honest, it is probably fine for this application for modern computers because, I mean, I forget how much data goes in one of these pages typically. I mean, obviously there are constants that we can adjust, but each block to uncompress is probably like a 20th of a second of sound or a 10th of a second of sound. So like one channel would be grabbing a mutex. I guess there's two queues, right? Input and output. So 40 times per second. So if you were playing 10 of these sounds, that's 400 times per second. With very little contention because very little work is being done. Well, you hope very little work is being done, but what happens if the array has to expand and call malloc when you add something? Then that's not good. But you could like pre-size the arrays to be bigger than you would hope that they ever get. Anyway, it's probably fine for this application, but like I'm saying, part of my job in making this programming language is making sure it helps with the harder problems that we need to attack today, right? And part of that is me getting better at serious parallel programming than I am. And so part of that is just gaining experience in these topics. So ultimately, that's the reason why I'm doing this. So I want to make a lock-free stack just to have one. And then I want to do a lock-free queue. And then I want to ship the lock-free queue in this game, right? You've basically only done parallel 4, parallel maps, which you're guessing is a higher level than what I'm working with. A little bit, yeah. I mean, parallel 4 is good for certain things, right? It's a very good low effort way to get some parallelism, right? And sometimes for some problems, if you're doing something embarrassingly parallel, then parallel 4 can be really helpful. But there's some classes of problems for which it's not really going to help you. Had similar audio problems with the cooperative scheduling in certain platform. Yeah. Anyway, I have a very small amount of experience with lock-free algorithms. I did do some way back in the 1990s probably was the last time, or maybe early 2000s. And I don't really remember anything about it, and I probably wasn't doing it right back then, to be honest. Although maybe. I mean, I was doing simple stuff. Anyway. I mean, let's look at this Java version, and we'll implement it, and then we'll make a test that, like, throws stuff at it, and we'll see how it goes, right? Where was the pseudocode version of the Triber stack? You mean, where'd it go? Here. Derivation, maybe deviation, of a scalable lock-free stack algorithm by Groves and Colvin from 2007. If this is the one you mean. I mean, this is just harder to read than the Java code. This is weird. Okay, this is a different algorithm, that's why. Because this one's doing more casses. So they're trying to do a better stack, I guess. I mean, there's like 4 casses here. So actually, one question that I have about the Triber stack in some of these lock-free data structure algorithms, there's a problem if you free and clear the node after you remove it. I'm going to assume that's not a problem here, but like it might be. I don't know. All right, so we're going to go to our foo file. This was the one. I deleted the rest of it from yesterday, but this is just spins up a bunch of threads and like does some things, right? For now, I think we're just going to spin up a bunch of threads, and yeah, they're each going to have some number of iterations, and we're just going to, for test number 1, they're just going to all dump stuff into the queue or the stack. And then at the end, we'll just grab it all and make sure it's all there, right? Okay. Let's just do 10 threads, 10 iterations per thread to start. And then we'll crank the number up. So we're going to go lock-free stack is a struct based on Triber's 1986 paper, Systems Programming and Coping with adapted from Java implementation by these guys. Okay. For now, we're not going to make this polymorphic. We're just going to hard code that the value is an integer. And we'll generalize it later once it works. Let's put this down here. Let's put it here. Okay. So we've got a node, and the stack has like a head. Oh, it's just got a top. So top is a pointer to a node. Great. So we want push and pop. So if it's empty, let's not call it success. It's called have a value. Okay. I don't know if this is the best way to do it, but whatever. Okay. Let's do push. Right? That was easy. New head is new node. New head.value. Incomplete supply and allocator. New head value is new value, right? Okay. And then while true, old head is stack.top, new head.next is old head, compare and swap. You know, I was been thinking about renaming compare and swap. Because we're calling all these things atomic whatever, so maybe I'll just call it atomic compare and swap, which is maybe a little bit redundant, but like all these things are called atomic underscore. I don't know, what do people think? At some point you should do some tests to see the performance of the intrinsics compared to what you had before. That is true. Did you read the short correctness section of the wiki article? GC is assumed, you think? Yeah, well, if that's the case, then we're sad. It was pointed out by Technic Beam that Java memory constraints mean that in other languages you need to do more checking because just checking the stack's top reference hasn't changed, doesn't guarantee safety. Yeah. Let's finish typing this in as a starting point, and then, yeah, like I was saying, I suspect that if we free the node, it's actually bad news bears. So maybe that's why the C++ implementation is longer. We'll take a look. I'm going to type this in, right, so that I've internalized it. It's very simple, but, you know, I'm just going to absorb it. And then, actually, let's not rename this yet, because it's a sidetrack. OK, so compare and swap. Stack.top, old head, new head. All right. This is lockfree stack.node because we're not, that name is not global. OK. So that's push according to the Java version. Oh, well, actually success. We've got to check this. If success break. OK. Pop. OK, this is weird. While true, old head is stack.top. If not old head, return false dummy. Let's just do this. Okay. Well, so according to Java, this is the whole thing. Now, there's all sorts of problems here. See, I mean, I have to go back and read the Triber paper, but first of all, it looks like we have an ABA problem, right? Where I could pop an item, free it, allocate a new item, and push it, and it's like a different item. Although maybe in this case that doesn't actually matter. Any ABA problem is one of the very common lock-free data structure problems that you have. Java is ABA free? How is Java ABA free? How is that even possible? Atomic add needs the atomic because you can also do a non-atomic add. The same doesn't really apply to compare and swap. Well, the machine instruction has a non-atomic version. It's just I don't know why you would ever use it. When you allocate a new object, it can't reference equal an old object. What? How do you not run out of memory under those conditions? How come when people mention a Jeff and Casey podcast, I never remember that one? That's a property only for atomic references. Well, I re-ask you, how do you not run out of memory under those conditions? Okay. So this Java version then is maybe not the best to work from. Let me see what Triber says. Go back to his paper, because he's the only one of these people that so far actually knows what he's doing. We add an allocation counter and use compare, double, and swap to detect the situation that gets us in trouble. Oh yeah, is he talking about ABA here? Yeah. Yeah. Fortunately, we implemented the double version of swap. We should maybe not call it comp exchange 16b. We should just call it double compare and swap. I don't know, man. You believe atomic reference has an allocation counter. I see. So that part of it is like factored away. Let's take a look at the C++ version. So now, technically speaking, this still doesn't solve the problem. Maybe it does. Maybe it does. Okay. Where's the C++ version? I got to put all these on the same browser. Too many browsers. Okay, C++ version. Try push. Why is he try pushing? Okay, what? Okay, so this is a different thing. Okay, so this node has a counter in it, right? Where is it? Why can I not, like, all this fancy highlighting is causing my eyes to not be able to parse the code. Node. Next, data. Where's the counter? Oh, does the data... New node with an item. Node pointer. Oh, I see. There's only one counter. The counter is not on the node. It's on the root. And he's putting that in something called node pointer. But the node doesn't use node pointer, right? Only God, C++, dude. Okay, what are these arguments? Tagged values node, like what? Okay. So this just has a node and a counter, probably. Is tagged value even a thing? That's like some general C++ thing that I don't know what it is. But I'm going to assume it just has a click raw. That's a good idea. It's also unreadable, but probably better. Have you looked at Concurrency Toolkit? It's plain C and has a lot of platform-specific stuff and optimizations. I haven't yet. Well, this one, Concurrency Kit, is that what you mean? Anyway, so these longer try push and try pops are for something else. Okay, so we're just going to say top is a pointer to node, and counter is an S64, right? Okay. Now these have to be consecutive. let's let nobody ever break that, right? Can I do this without instantiating something? There's probably a simpler way to do that. Do we even compile? We haven't checked to see if we compile in a while. Undeclared identifier new head. All right. Return true old head. Right? Maybe we should set old head.next to null for sanitary purposes, but oh, that value. Okay. So we're not actually using any of this. We got another shut up, not all controlled head, return a value for now. We need to fix that. All right. So that's great. So we've got to use this index. Let's call it, what should we call it? This comp exchange 16b is a sucky name. Let's call it double compare and swap. Or compare and swap 2. What's the standard name for this? We've got all these resources to look at. Okay. Compare and swap 2 electric boogaloo. That's pretty good. Let's call it compare and swap 2. So we're going to have to go edit the compiler and know what the hell that means. Compare and swap 2. We could actually make this polymorphic and like test the old value versus new value. You know what I mean? Like old value and new value have to be the same type, but different types for each slot. We could do that. Not yet though. Let's make it work. And then we'll do that. So we want to compare and swap to so the problem is we need to serialize these things somehow. Like so we could say like old serial just call it serial. Okay, old serial is stack dot serial, right? And I don't think this will work without some kind of strict ordering, right? So old serial right? So the thing is, no, maybe it doesn't matter. Maybe it doesn't matter. Like, if the compiler reorders all of these things, see, these have to be read simultaneously, right? Because if they're not, then this doesn't do anything. Because you could have swapped Am I wrong about this? Again, this is me learning to think better about lock-free stuff. Oh, it's Lana's stream. What up? Party of 66. What's up, people? You could technically starve your thread with a design like this, but it's not going to happen for any usage pattern that we have. Party of 66. Get your kicks with a party of 66. All right, so somebody tell me if I'm wrong here. Like, if these are not read simultaneously, then it's not actually useful. to have two values. Am I wrong about that? I'm not wrong. You need a 128-bit atomic read. I don't think I have a 128-bit atomic read. So let's see what Tribert says about this. The good logic is shown in figure 11 on page 20. So increment value, new counter value, count of gets. Oh, wait. When we push, we don't do a counter. The counter is only for the number of gets. Hey, Lana's people, do you like my nice 1980s? Okay, look, this is a 1980s research paper, but it looks like a 1960s research paper. That's all I'm saying. Okay. Yeah, no, there's no dot calls in this language. No. No, it's not about hating it being related to object-oriented programming. It's about not making the system more complicated than it needs to be to do what it actually does. The mental niceness of thinking about A dot B whatever is not worth the amount of constraints that puts on your programming language, in my opinion. Okay, so let me see why this guy doesn't need. Oh, okay. This is compare and swap. This is compare double swap. So he doesn't do an atomic read. Where does R5 come from? Oh, load R5 with 1, add R3. LM. Is that a double read right there? First element, comma, counter. Yeah, so he has a double read. Jerk. Here's something you want to save for later when you do queues. Okay. That sounds good to me. Michael Scott from The Office telling us how to do queues. Isn't that the guy's name? I've only seen like one episode of that show, 2 episodes. Okay, so we only need a single value cas. I've got so many things open right here. He only writes the next pointer here and ignores the value. Okay. Single compare and swap. Okay. Compare and swap to Okay, so this needs to be an atomic read right here. We don't have that. Well, we do. We could emulate it with a compare and swap 2, right? We could do a compare and swap 2 of the values with the same values, right? I would rather not hack that, though. In x86, normal loads are atomic in that sense. Well, normal loads of one thing, but not a 128-bit load, right? So you can 128-bit load into a vector register. I mean, I need something. I don't have anything right now to do that. So we need something. Okay. Well, they're saying comp exchange is the only way to do it. So we'll do it. So emulate a 128-bit load by using cas2. All right. So we're going to say old head is a lock-free I think I can just do that. Don't even know my own programming language. Because the thing is, I don't want to say lock-free stack.node. I could say that now, but eventually when this becomes a parameterized struct, if that's the way that we do this, then it won't really be meaningful to say lock-free stack.node, because it's like, which lock-free stack? We don't know what the parameters are. So yeah. Old head is that. It's the type of that. Old serial is, let's call it U64. Screw it. And then while true, old head is stack.top. Old serial is stack.serial. Compare and swap to stack.top. Old head, old serial, old head, old. This seems really stupid, but that should do it, right? Somebody tell me if that seems wrong. This will break after 18 quintillion pops. No, it may break after 18 quintillion pops. It'll break if you pop a node, free it, reallocate it at the same address, and re-add it exactly 18 quintillion pops later. Yes, then it will break. Okay, nobody's complaining about this. Remember, I'm jet lagged. I'm not thinking properly. As if I ever think properly, but okay. So we do that. Okay. So that is what that does. Then if there's no old head, we return false. New head is old head next. Success is cast 2. Old head, old serial, new head, old serial plus 1. If success, return true. Okay, wait. Yeah. I guess, man. There's also a thing called the ABA problem where reused memory goofs things up. That's what we've been talking about. That's what this serial number is there to solve 18 quintillion pops later. I think we're gonna institute a robot that auto bans anyone who talks about object-oriented programming. Like, that's how bad things are. Can't you just remove the inner loop? If old serial doesn't match old head, the outer compare and swap 2 will fail. Wait. Can't you just remove the inner loop if old serial doesn't match old head? The outer, this one, I guess, will fail. No, because the problem is you might get the ABA problem again. If you don't ensure that these two match each other atomically, you'll get the ABA problem. I don't think you can get rid of this loop. I don't think. I mean, okay, but one thing we can do, so let's put this out here, right? And then we can actually turn this inner loop into the outer loop by doing this. Get new. Right? Right? Does anyone see a problem with that? Don't you get an atomically loaded pair out of a single cast 2 no matter what? No, so cast 2 does not return the old values, I don't think, right? Or at least we didn't make it do that. So comp exchange 16b, yeah. Comp exchange 16b does not give us any output about what was in M128. we just get the 0 flag. Right? Oh, if it doesn't match. Okay. If it doesn't match, we get that. So the question is, how can we force it not to match? I mean, you could use a serial of OXFFFFFFFFFF. But we don't return that data right now. Rcast2, and this may be a limitation, we may want a different intrinsic that provides all the return values, but Rcast2 doesn't say what the old values were. Does the second compare and swap to not check for both values being correct at the same time? It does that, but that's not good enough, right? Because the problem is we have to make sure see, the problem is the following. Let's copy this code for a second. So again, we have to be more paranoid than Treiber did because we have to deal with LLVM trying to screw us behind the scenes and stuff, right? So if we just do this, which I think is what you're saying, right? Non-atomic read of these that then gets cast down here. At the very least, what could happen is the compiler goes, oh, I'm going to move this down to here because we don't need it till there, right? So we've like evaluated new head and then gotten the old serial afterward, right? And between these two lines, the node could have been grabbed, freed, reallocated, and re-added to the list. So the serial number we get is like the wrong one anyway. Now the question then is, though, like the problem here is, oh, I guess we don't write to the node. Oh, never mind. I mean, between this and forget even the ABA problem. Between this step and this step, just say somebody pops the head off, right? So there's a new thing on the head of the, no, because that'll fail here. So when pops the head off, pops some other nodes off so that, pops two nodes off so that old head.next is invalid now, right? Reallocates head, re-adds it between this line and this line. Then old head still matches, right? And old serial matches because you just got it after it was re-added, right? But new head is not valid. And so we're pushing an invalid node onto the top of the list. Okay, that's compiler reordering, which is not what Treiber was dealing with, and he still felt the need to make it an atomic read. He explains in his paper why, which I don't remember the explanation. Maybe it wasn't an atomic read. Maybe it's just a double read, but I think it was an atomic double read. Why return dummy and not just 0? It's because later on this is going to be generic, right? So if you say dummy colon t, then you get whatever the default value is for that type, right? Really, we want to be able to say, so we have default values for return values. So up here we could say int equals 0 and then not bother saying it in this case. We could just say return false. The problem is, when we make this generic right now, we don't know if 0 is a valid value for whatever this type is. So we'd like to, at some point, be able to say like equals default or something, but we don't have that facility right now. So I'm just planning ahead a little bit to when this is genericized, is all. It is lock-full programming, you're right. An atomic load intrinsic would prevent the compiler from reordering even though it lowers to a normal load. Didn't Casey implement a lock-free queue for Handmade Hero? He might have. This is just me learning, man. I'm learning on stream. I'm not too old to learn things. How about using something like underscore as a shorthand for I don't care, just create a default value for the type and return it? That might work too. That might work. Do I think the compiler will become as complicated as C++? No, not ever. Not ever. If one thread runs old head equals stack.top, and another thread pushes ahead at the same memory location on the list before the first thread, you would end up reading the first day. Right, okay, it's a good point. So here, exactly what I said could happen with this reordering could happen here, right? You could ABA right here. Actually, no. If you ABA right here, so old head gets pulled off by somebody else, freed, reallocated. The thing is, because it's an ABA, your pointer is still valid. There is a problem with this, though, that I don't think any of this solves, all right? I don't understand how to solve this. Somebody tell me how I could possibly solve this. So here we go. We get these. We do a CAS. We verify that these were atomically loaded, all right? We verify that old head was not a null pointer, okay? Here's my problem. Between here and here, old head could not only get removed and freed, it could be on a page of memory that gets unmapped, okay? If that page of memory gets unmapped right here, this will fault. right? I don't understand how you're ever supposed to avoid that. This would either be, you know, an uninitialized memory read or a fault. I don't know how this can work if the OS is allowed to reclaim pages. Do you know what I'm saying? Because the safety mechanism here is just that hey, if old head changed, then we don't do this. But there's nothing to prevent us from doing this. So like really the only thing that would make this correct in the presence of unmapping pages is if we somehow read oldhead.next in the same atomic operation as this one, which I don't think is possible, right? I think you already figured this out, but if you do complex 16B with the same expected new value, you get a 128-bit atomic load. Yeah, that's exactly what I'm doing here. See, old. Yeah. But I'm saying this still isn't good enough. Atomically reading these is not good enough because I could page fault there. Unless you guarantee that we never unmap memory. Why would you care about that? Because if your default allocator is malloc, that'll just happen. What do you mean, why would I care about that? So why is old head being freed from under you? Because somebody else called pop while I'm calling pop. Between, like, say when I'm right in here, I get preempted and somebody else calls pop. Okay. And gets rid of my node. Then I dereference it here and the page is unmapped and I die. So don't use malloc, maybe, but I mean, I personally probably wouldn't use malloc, but this could happen with anything. So like, most allocators that actually free RAM free pages. Defer to caller, it's the usage code's responsibility to use the data structure in a context in which it makes sense. Maybe, but like what does the C++ version do about this? They probably don't do anything about it. What could they possibly do? Dude, we've got so many. I mean, what does the Rust one do about it? Managing garbage. Service shared by all data structures. Oh, God. Each thread keeps local garbage lists. When a thread marks a node as unlinked, that node is added to some thread local data rather than immediately to a global garbage list. Each current thread will check whether its local garbage has surpassed the collection threshold. If so, it will attempt a collection. Because GC can only occur if all active threads are on the current epoch, it's not always possible to collect. It doesn't solve the problem because you can replace unmap the page with overwrite the next pointer, and you have the same problem, right? No, no, because if you overwrite, the only case in which you would overwrite the next pointer, where even are we? The only case in which you would overwrite the next pointer, you would increment the serial number. That's the whole point. So if you overwrote the next pointer right here, this cast would fail, okay? That's not the problem. The problem is when this is illegal. We need to get Casey in here to tell me what the hell he does about this. A pointer in C++ is an abstract reference to a referent. What do you mean, what do they do about it, lol? Yeah, exactly. Exactly. Can you use a lock, or is the goal not to use lock? The whole point was not to use locks. If we're going to use locks, then yeah. I mean, I could, so for the use case that we have, I could just never free the memory. Because, well, I don't know. I don't know, man. Wait, if you've got old head and it's not null, then at that point, the only way for .next to be unmapped is if this data structure is not a stack. Not true. Not true, because if we're right here, let's call this danger zone, right? Let's say we fly into the danger zone, and then we get preempted by a different thread, and that thread calls pop and grabs the node that we were going to grab, right? Does some stuff, frees the node, and that's the last thing on a particular memory page, causing the page to be unmapped. Then this is illegal when we swap in. Do you get what I'm saying? How many hours a day do I work? It's kind of random, but I work a lot more than most people. Right, so this is the thing is, don't get confused about this. Here we've loaded the value of old head, but we haven't changed it, so anyone else could also load the value of old head. Right, that's the thing. Anyone else could call pop and do this whole thing while we're sitting here with our thumb up our butt. Change the first compare and swap to swap in old serial plus 1. Then write if old serial and 1 continue. What? That doesn't solve any problem. Explain to me how that's supposed to solve a problem. This calls for a paint session. How have we been affiliate for 11 months? That doesn't make any sense. The Java example in Wikipedia does not do anything in that danger zone. Another thread can't grab it, you've cast it. Cast is not a lock. It's a lock-free data structure. It's a lock-free data structure. Anyone else can do anything they want. That's the whole point. You think he used ticket mutexes? Oh, Casey did? The only way I can think of to safely read through a pointer is to exchange the pointer with null. and make other threads wait if it is null. Right, which if old serial and one continue goes before the compare and swap, if another thread is currently working in the danger zone, then this thread cannot get there until it's past the danger zone and increments old serial again. Maybe. We probably should pause in our continues, but I mean, it is a lock, but at least it's a cheap lock, right? I'm not sure that there's a lot of practical difference. Sure, if contention is low. Well, I mean, so what's being suggested is to do this, right? This, and then if I understand correctly, we say if old serial and one continue, right? So let's put parentheses around there for clarity, right? So if somebody is here, actually, the check for old head can actually go outside also, because if it's ever null, then hey, there was nothing there this time that you checked, right? I think. Well, yeah, anyway, it doesn't matter that much. So the point is, I mean, how is this that much different from this, honestly? And I guess the answer is that if somebody wrote a value, then when this failed, they're already done writing the value. And so you're guaranteed to be able to proceed unless somebody else writes a value, right? Whereas in this case, you don't know when this is going to stop being true. I mean, it's true for this too, but by default, if somebody else is sleeping, this will not be true for a long time, right? So that's the difference, I guess, is in this case, yeah. Just go with ticket mutexes like Casey. Somebody link me this paper that you're reading about memory reclamation. Oh, there it is. Only 25 pages. I'll probably read it later tonight. What year is this? 2018. New algorithm for gathering local roots. God. I mean, I'll read it, but it sounds heavier weight than I want to. But this sounds a lot like what that Rust guy was doing. Why can I not drag the scroll bar? Dude, fucking Windows just keeps getting worse. Just can't drag the scroll bar on my $4,000 computer. Thanks, guys. See the end of the first intro paragraph. Many lockfree data structures are published without any memory reclamation support, as it was assumed that the application is short-lived enough that all memory is allocated in advance. This prevents the use of such data structures in real applications. Yeah. Paper sounds like it's suggesting a basic mark and sweep garbage collector for unreachable nodes. Yeah, I mean, I know how to write a garbage collector. And that sounds like what the Rust guys did. Well, they said the title of this one is without garbage collection, and then they say managing garbage. So I don't trust this just because he made a cool name for his library. Like, I just don't trust that. Common sentiment seems to be that if you write the garbage collection yourself, it's not a garbage collector. Yeah. Second compare and swap doesn't even have to be a compare and swap with the parity check present. Well, don't you want to make sure that you write the serial number at the same time as you write the new head? It has to at least be an atomic store, right? It has to be an atomic 128-bit store. Second cast. Oh. I mean, we're not going to do this. We're just illustrating. You're right. That would fail. If you could set the head first, that would be sufficient. No. That wouldn't be. It doesn't matter. It doesn't matter if you set the head first or second. Basically, there is no legal place to put this line anywhere. Anywhere in the entire program, that line will die sometimes if you're allowed to unmap pages. Reclaiming nodes when no threads are in pop. Yeah, so you would need I mean, you could even put that like you could check for reclamations anytime somebody calls pop or push, right? But I don't know how to do that without essentially having a lock. I mean, we would essentially have a second free list on the stack. Okay, and when we're going to free something, we put it on the second free list. Yeah, and we somewhere have an atomic counter of how many people are in pop. If there are 0 people in pop, the problem is you have to set a lock somewhere, right? So if there are 0 people in pop, open brace, do the free. While you're doing the free, somebody might enter pop, right? Although no, okay, you know that they weren't in at the beginning, so they can't have a pointer to the thing because it was on the free list. Okay, I buy that. I mean, that's going to complicate this even more. I don't know if it's worth it at some point. The C++ implementation mentioned above frees the nodes on the free list if there's only one thread in pop. Otherwise, adds it to a free list. Read comment above. Yeah. I mean, this is going to be complicated enough that it's hard to think about, but all right. So for now, we're going to build a test program. We don't even free right now. If we don't free, then danger zone is not dangerous. So we're going to do a version that doesn't free. We're going to build a test for it, make sure it seems to work. And then we'll try to do the free list version. And I might get too tired before we do that, because again, I'm super jet lagged on little sleep. Is there a way to turn off instruction ordering in LLVM? There must be, but I don't know what it is. If you are the only thread in pop, you take ownership of the free list and have to check again before you know it is safe. Otherwise, you need to put them back. Right, because somebody else could start looking at the free list while you're looking at the free list. No, because you use a CAS to swap the free list with null, right? That's how you would get the free list. I'm not sure why you would need to check and put it back. Like, I feel like if you cast to get the free list, then you're good to just free everything in the free list. I'm not sure why that wouldn't be the case. I'm not saying that I 100% believe that it's not necessary, but yeah. You missed the beginning, but if serial is only used for the pop check, you could just use the low bit of head as busy flag. of head? What? No, the serial is to prevent ABA. Don't you need to atomically swap the free list pointer along with whatever operation tells you you're the only thread in pop? No. No. Well, actually, yes. Okay, so the problem is, right. The problem is, what if somebody enters pop and reads a pointer after you check that you were the only thread in pop, right? So you need to check the value, make sure it's 0, and then double cast 0 and the free list pointer with 0 and null. And if that succeeds, then you free the free list. Right? Free list fixes the ABA problem because things can't get reused until they can't be referenced. No, that's not true. That's not true. Is it? Okay, I guess right. You only free things if you're in the middle of pop and nobody else is contesting. All right, I buy it. So that'll be good because that gets rid of the serial number. And getting, okay, I'm starting to like this, right? Because if we can get rid of the serial number, then this cast goes away again. And that simplifies this down. And then we're going to add some complexity with the free list stuff, but we at least bought some simplicity, right? Like this turns into a single cast. And this says, so this becomes, you know, if not success, continue, right? Just retry everything. And then down here, maybe try to free the free list, right? The problem is, how do you put the guy onto the free list? Actually, we do this first. Put the guy onto the free list, and then we'll try to free the entire free list. I mean, that's kind of stupid, but it's simple. Right? Okay, so if we believe that, then let's do this. Let's get rid of the serial. We're going to need another number in a minute, but so we get rid of this entire cast. We get rid of that. Okay. So that's a single cast. Okay. So we're just going to drop back to this. We're going to do this version without freeing, make it appear to work, and then we'll add a free list. Free list just has push and take all operations, which are easier than pop. Yeah, I dig it. Okay. Oh, we get rid of this here. And you know what? We don't have atomic decrement, so we would do atomic add with -1. Maybe this means we want to do atomic decrement. We'll just do this just for now, just to keep track of it. Oh, we can get rid of all this stuff. However, we might need an equivalent for the frickin' free list. Okay, we're just going to put those there, and we're just going to do it here. Atomic increment num threads in pop. We don't have atomic decrements. Defer atomic add num threads in pop -1. It might be better to do the increment here and the decrement, I mean, here and there, or after the CAS? I don't know, right? To be maximally paranoid, I'm going to do it here, but you need fetch and decrement anyway. Does defer executed at the end of the current scope? Yes. Yes, it executes it at scope close, which in this case would happen here and there. Dude, so much stuff just to guard, like, this is all we're guarding, essentially. And, like, you need so much armor to guard that. It's crazy. Okay. All right. Let's get this compiling again. All right. Oh God, it's a U64. All right. Well, now we should do something. Okay, so in our thread proc, okay, we're going to we're just going to have a global variable. because that's how we're writing. And these guys are just going to talk to the global variable. Instead of atomic increment the counter, so we have a data, a void star, job info. We'll call it job info thread.data or info, right? We're just going to say starting index is int, count is int. And this guy is going to say when he starts a thread, it dot data is new job info. It dot starting index is starting index. It dot count is iterations. Starting index plus equals num iterations. So each thread is just going to count a range of integers, but the integers are going to be unique, right? I'll just say 0 explicitly. So the whole point is we're going to want to make sure that all the integers in the range for all the threads are present in some order in the frickin' thing. All right? Okay, so we're going to say push onto the stack and add that to the starting index, and we're just going to push that on the stack, right? So the first thread will do 1 to 10, the next thread will do 11 to 20, and so forth. It's a little weird because starting index is 0, but then we go 1 to blah, blah, blah. Now let's make it this. So we're adding 0 as well. Okay. Starting index is not a member of thread. It's because we're going to make a job info. And info, we're putting it on the thread. You know, why are we going to be job infos num threads job info? Like, why be a butt about it and call new, right? So info is job infos index, and then there we go. Starting index, count is num iterations. Yeah, okay, something like that. Why do I keep not fixing it? Info. Heisenbug. Okay, well, we run. And after all the threads are going to be done, first thing I'm going to do is just print out all the values. Node is stack dot top while node print the number, and node is node dot next, right? There we go. It's not going to be very convincing. I mean, we've got a bunch of numbers, right? Do we see 0? They're at least, they're kind of mostly in order by tens. Oh, here they start getting scrambled more. All right, so we're going to increase the number of iterations. Here's what we're going to do. We're going to take the sum. Sum is 0. Sum plus equals node.value. All right, node is node.next. Correct is num threads, or we'll say n is -1 because we're starting at 0. And correct is n times n plus 1 divided by 2. All right? And counter is sum. Let's call it sum. Right? You guys remember your high school math, right? High school math. If sum is equal to correct, we print success. Otherwise, we print failure. Hopefully, I did that right. Success. Bam. Bam. All right, so now we add more threads because we're not printing it out, and more iterations. Or let's do 10 threads, 1,000 iterations. That might be a really big, I mean, I guess I believe that. It's going to be 9999 times 10,000 divided by 2. Yeah, that looks about right. All right. 9999 times 10,000 divided by 2. Okay. So, I mean, it looks like it's working, but that's not very surprising because nobody ever calls pop. So, we need to do that now. We need to make one of the threads the following. Okay. If its index is less than num threads -1, the last thread is the popper index num threads -1. Okay, so if it's less than num threads -1, we do all this stuff. Otherwise, we just leave that empty. And you know what? We're gonna okay. So this n is going to be num threads -1, right? Actually, this should still, let's make sure this still works. Okay, yep. We have one less thread working, so the number is lower, all right? So that last thread he's the popper or the pooper, right? How does the popper know when he's done? Why don't we just, let's just have the main thread be the popper. You know what? Screw all this stuff that I just did. Let's do something simpler. Okay, do we still compile? Yeah, okay. So we're going to be the popper in here. So here we're going to pause, right? So we still work. That's great. We're going to just pop some nodes. While true, I'm going to do it here. While true, node is pop stack. If not node break, actually it's not node is pop stack, it's value, right? Pop returns the value. Have a value, comma value, right? If we have no value, we break. Yeah, why didn't I use pop here? We should have tested pop. I just didn't. Okay, if we don't have a value, we break. Otherwise, sum plus equals value, right? This goes here. So we're doing that while the threads are giving us things. Now, this isn't as aggressive as having a lot of consumer threads. If we were going to do that design, I'd have a variable number of producer threads and a variable number of consumer threads. So we'll upgrade to that next, but we want to make sure this works first, right? Failure. That's not good. Okay, well, let's do it for one thread, which actually still might not be good. Okay. I'm not sure why this doesn't work. Okay, with two threads it doesn't work. What about with that many iterations? Also doesn't work. Well, if it doesn't work already, it's certainly not going to work if we make it more complicated. Hopefully it's just a dumb bug. We seem to always be overcounting. Like Alec Baldwin and Glenn Ross, always be overcounting. This just motivates you to stay away from lock-free for as long as possible. So like I said, we never tested the pop version of adding the numbers. So like, let's just do the thread stuff like we were doing it. And then once we know all the threads are done, we do it here. So let's just verify that this is going to do the right thing. Yeah? Heisenberg. It does do the right thing. So we have a concurrency problem. Well, oh wait, let's turn up the threads and make sure, but I think it's going to be fine. Yeah. So we have a concurrency problem that we would rather not have. Oh! Wait, no. Okay. The problem with this one is that there's at least one bug. I don't know why we would be overcounting, but there's at least one bug where we would add some guys up and then we finish all the threads, but we haven't popped the last few guys, and then we exit this loop, right? So we actually, for this design to be correct, we need to do this both places or something. Like we need to make sure we add up everything after the work is done. Now we're overcounting by even more. Wait. Why? Why does the native code one work? Oh boy. Out of sheer curiosity, could we check whether the cast and the pop ever fails? Oh, I see what you're asking. Yeah. Okay, so this is very weird that the compile time version is working, or not working, and the runtime version is working. The runtime version is up to date. So it's either due to timing in some way, or maybe our intrinsic is broken in some way in the compile time emulation. That's a possibility. Does Shroud yell Twitch Prime anymore? That's so 2018. I thought it was Justin who yells Twitch Prime. Come on, bro. All right. So I am not sure what to think here. Maybe our CAS is broken. So one thing I could do is make the threads all frickin' sleep for random amounts of time and try to get, because maybe the runtime version breaks because it's too fast, right? So I can go sleep milliseconds 1. So I don't know how long that's going to take. Whoops. Oh boy. The compile time version. All right, so 100,000 milliseconds for one thread is 100 seconds. Let's not do that. Okay, so that fails. That succeeds. I'm starting to feel like the intrinsic might be buggy. Like, how probable is it that it's just a timing issue? I mean, I wonder if this screwed with us somehow. That would have to be a really strange bug. I don't think that's the case. No. It's so weird. We're overcounting by like 10%. Do you have any method for ensuring correctness of multi-threaded code? Not currently. Not currently. Okay. Does this break? So our consumer is just in the main thread. So does it break with just one producer thread? Like, is the bug in the producer or the consumer? Okay, yeah, it failed. It failed at compile time with just one producer. That doesn't really still tell us whether the bug is producer or consumer, though. Okay, so we didn't really need this, right? Fails anyway. We were just doing that to see if we could get this one to fail, and it doesn't. So the first test pretty much told us that the producer was working. Yeah, I guess so. I mean, well, not necessarily. So the thing that breaks it is when we pop while people are pushing, which could be a bug in push or a bug in pop, honestly. You know what I'm saying? I mean, I probably just messed up pop a little bit in all these changes that we did. Let's look at it again. Old head. If no old head, return false. New head. Cass. Old head, new head. If no success, go back. Return true, old head. I mean, it looks fine. Okay, if it's a bug in the implementation of the intrinsic, I could try compare and swap 2. I mean, maybe there's the same bug in both of them, but I think they're a little bit different. We can try compare and swap 2. Old head 0, new head 0, right? And old head 0, new head 0. It should be functionally the same, but going through a different code path. You dig? Yeah, well, XX, 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 XX. Why are we crashing? That's weird. Well, we crash in both. What? Stack that top needs a dummy 0 after it. It does have one right here. I did not forget this. A 0 value to pass to compare and swap. It had better be. If it isn't, we can't use it for many applications. Well, so I don't think I can run an LLVM because we don't have compare and swap 2 there yet. And that would be the easier way to debug. So we're going to do the compiler, and we're going to see why we're crashing at compile time. If it takes a pointer, it's going to be reading. No, these are values. These are values. This is the address. These are values to put in the address. Int is probably 32-bit. It is 64, yeah. It is 64, okay. It is mega 64. Access violation. Dest. Okay. That's all valid for 16 bytes. Comparand is okay. Oh, it's not aligned probably. It's not aligned. No, it should be. It's at the top of the struct. Do I have an align directive? I think I do. Maybe we never added that yet. Okay, wait, I can just check the add. Okay, let's at least determine that this is the problem. Yeah, destination needs to be 16 byte aligned, and it isn't. So let's fix that somehow. Let's put this on the to-do list. Struct alignment, declaration alignment. Because especially when we start doing like AVX intrinsics, we need to control alignment of stuff. Okay, so for this, we need to force stack to be 16 byte aligned. I mean, I think if I make a member 16 long, maybe that doesn't matter. I don't think that matters. Yeah. Let's just put an assertion. So that's going to fail. Assertion failed. Okay, so, okay, this is really dumb. Okay. Stack memory size of lockfree stack plus 16 U8. Right here, this is dumb. Give us a way to control alignment, please. Mem is stack memory.data. Mem plus equals cast U64 mem mod 16. I mean, that'll add 16 if we don't need to, but that should be fine, I think. Wait, what? Oh, stack equals XX mem. I didn't do it. What? How am I screwing this up? The answer is the same way I always screw it up. Oh wait, add, okay. I didn't change these. Ta-da! All right. There we go. Okay, we run again. We still fail. We fail by a lot less than we used to, which is small consolation. We still fail. And we succeed there. I hate to say it, but I could malloc. That's a good point. If I just, yeah. If I just say, actually that's better because we actually run the constructor here, which we weren't doing in this case. Which right now doesn't do anything except set things to 0, which we already would have gotten from this. But if we ever added something to this, we would have been confused. We also could have just manually run the initializer. It's fine. But whatever, man. Okay. So we definitely need alignment primitives, but we're not going to rat hole on that now. We really are failing by less, but we are failing. I'm tempted to think that that isn't a problem in the intrinsics, but I don't actually know, if I'm being honest. Like maybe cast 2 is just slower and that's why we're off by less. But it's fine. I mean, that's the weird thing, is it's fine in native code. Size 8. Old value, new value. Interlocked exchange. Success equals result is equal to old value. Is that really right? I mean, I guess so. I mean, what more do you want? It's very weird. I mean, this one just gives us a Boolean. Like, how do we screw that up? So I'm kind of inclined to believe that the problem is not in these intrinsics unless I'm doing something really weird. The thing is, a well-designed lock is also really fast under low contention, so it's not automatically true that lock free equals faster, even in that case. True. That is true. Well, I am starting to get tired from the jet lag, so I might pop a melatonin to make double sure that I go to sleep at the right time tonight, and then continue this later. So my suspicion is that the code is wrong and not that the intrinsics are wrong. And we're just getting lucky at runtime because the timing is different. However, because the implementation of the intrinsics is in principle totally different, I mean, it could just be that the intrinsics are wrong in the bytecode. I don't actually know. It could be that the intrinsics are right and the code is right, but there's a problem in the bytecode interpreter where it's not handling multiple threads correctly, right? So that could also be a frickin' thing. Like there's just some state variable that causes us to like skip something. It's possible. Try running once with the sleep milliseconds. You mean the one that was here? That one? Still overcounting. Although, let's see if the amount of overcounting goes down or up if we do more sleeps. 5008, 501, 501. It appears to have gone up. 502, I mean, 5018. It's not really that big of a difference. 502. Let's go 200. No, it's the same. Heisenberg. Someday I'll fix that, I swear. 5003 though. 501. Yeah, I don't know. Wait, is it getting the same value? No. No, okay. 116.926. Does it still pass with a compiled version? Foo. Yeah. I mean, the compiled version is just great. Does it still pass? Does it still work in compiled code? Yes. Does it still fail with very few iterations? Well, I doubt it, but let's check it. I mean, this is only with one producer thread, which is the nutballs thing. So at least we know that it's not push interacting with push or pop interacting with pop. If it's the code, it's push interacting with pop. That does narrow it down a lot. All right, 100. Oh, you know what? We're not going to be sleeping very much at 100. So okay, we got to fail at 100 iterations. Let me take out this sleep. Okay, we got to fail. We don't all the time get fails, but we get them once in a while. Well, now we're getting the Heisenberg more than we're getting the fails. It's bad news. We just got a lot of fails. Let's see if that helps. Heisenberg. Bro, this is why parallelism sucks. Oh, 5002. We got to fail on the 11th run. Okay. I don't know what evil mode is. So the runtime version succeeded 30 times in a row. Fifty. So 100 iterations is enough. Let's see if it goes up with 100 divided this way. Boom. Boom. Okay, it's failing a lot with 2 threads. Okay, so we could, I mean, let's try 2 and 25, right? Okay, fail. Wait. Yeah. Let's try 2 and 10. 10. Awesome. Okay. So we can debug this by just printing the frickin' numbers as we get them. And seeing what happens. I mean, that's going to affect the timing as well. Okay. So we got them all before the threads stopped. We're over by 10. I don't see 2 10s. Oh, 1, 2, 3, 4, 5, 6. There's another 4, 7, 6, 8, 9, 10. So 6 and 4 were duplicated. So how do we duplicate numbers if there's only one guy popping? Well, one of the guys pushing somehow pushes what you pop back or something. If you have to, you can put the pop returns in an array. True. I mean, I could just put them in the free list, right? Because we were going to need to do that anyway. Can you debug the node address in pop to see if it's the same address? Well, not currently, because we don't return the node, but we certainly can return the node. Whoops. Let's just put a default value on that. Okay, so now if we ever return a value, we return it, the pointer, whoops, capital node. Okay, so then okay. Same thing down here. Well, we have Heisened our bug. So it may be a bug in the bytecode interpreter having to do with multiple return values, for all I frickin' know. Like it, and that bug maybe doesn't exist in there. Or maybe it just changed the timing. This is what's fun about this kind of bug. Okay. Or maybe these prints are just too expensive now. Sure looks right. I'm starting to doubt that it's timing, and I'm starting to think it's a return value bug in the bytecode interpreter. Like, let me just take that out. So we're ignoring the return value. It'll still get returned, we just don't pay attention to it. Success. Success. This is good news though, because if there is such a bug, it could be the cause of the Heisenbug. The other Heisenbug, not today's Heisenbug, but the regular Heisenbug that I keep swearing that I'll fix someday. Because it could affect anything at that point. So here, we don't ever, now we don't ever return it. We still return it though, because we return 3 values always. Success. But if I just do this, failure, failure, failure. Have a value. P is cast pointer U8, address of have a value. Assert P is equal to 0 or P is equal to 1. Am I getting a garbage value back? Type mismatch. Oh. Let's just do that. Well, we're not asserting. So one thing I was wondering is like, is the return value getting spammed? It is not getting spammed. If it is getting overwritten, it's getting overwritten with 1, which seems very unlikely. Because the only way we can fail is if our cast returns 1 incorrectly. If it returns 0, oh no, we could fail if it returns 0 as well, because that would mean that we write the value and don't think we wrote the value, which could screw us up. That sounds a lot more likely, like accidentally stomping the return value with 0. Okay, so like just adding a return value fixes the bug, which like we could then go on and continue working on this, but this bug in the bytecode interpreter is important enough that this would become top priority, because if you're trying to debug lock-free stuff and something like this is happening and you don't know when it's going to happen, you just go crazy. Okay, so we have to repro this. I'm going to end the stream there, though, because I want to repro it when I'm not super tired. Does it happen if pop has one return? I was going to check that. Okay, let's check it. Let's check it. Let me get a melatonin and then we'll check it. Because you're supposed to pop that a while before going to bed. Yeah, that's what I was going to do, is return -1, because we know that we're integers only right now. All right. So instead of have a value, we're just going to return -1. Okay. So when we call pop, what just happened? Okay. We fail. Do we fail with fewer threads? Yep. One thread success, 2 threads fail. Yeah. Yeah. So I'm thinking bug in the bytecode interpreter. It could be algorithm timing, but that seems hard to believe. Look, it succeeds now. With, well, Heisenberg. Oh, no, it fails with 10 threads. Huh? But that also like implies that it's not really timing, because the timing would be pretty close between this and the other. I don't know, man. I am not sure how to investigate the possibility that this is a bug in the bytecode interpreter, as opposed to timing. I will have to think about that. You feel like the stack is getting clobbered. See, now it's not mattering. That's so weird, dude. Maybe it has to do with returning a bool as the first argument. Somehow. I don't know. A bool is the first argument, and a non-bool is a later. I don't know. When is defer for atomic add called? We're not using that. This actually doesn't matter at all. We're not using this variable. I mean, unless that's overwriting something horrible. Oh, you're saying that might be killing the stack in some way? I don't think so. But since we don't need it, we might as well get rid of it. Wait, why did we put a sleep in pop? That's weird. I meant to put the sleep here as opposed to here, but whoops. Probably doesn't matter. Or maybe it does. Okay, here's my thing for you guys. Maybe it's timing, or maybe it's that sleep milliseconds calls a win API call, and we don't do the calling convention correctly somehow, although we should. And that like hoses the stack in some way. You know what I mean? I mean, we could change this to an intrinsic, which isn't going to be that different, but it will be a little bit, like this goes through the FFI path, and this is something the bytecode interpreter knows about. So, I mean, a pause is very small. Okay, well, maybe it's timing. Like, what if we just don't even do this? What if we just pause a bunch right in here? Bro, this is so weird. Wait, we're not even incrementing it. Hold on. X plus equals 1. Fails. Okay. This is weird. So here x is 0, so x mod sleep is always 0, so we should be pausing every time. okay? But if I do this, that should be the same apart from spending time in the if, and we succeed. Like, really, guys? Sleep is 2 and x should be 0. This succeeds. Okay. This fails. Riddle me that, Batman. It's not even a static variable. That's just on the stack right here. Let's put it in global scope. Fails. Oh, okay, no, never mind. Okay. This is const expr evaluated, so it's different. We don't actually do this mod during bytecode. So something about that if statement. I wonder if statements are broken and like we're skipping over an instruction sometimes. That would be amazing. I wouldn't put it past myself. Try division or something. Well, we could certainly do div instead of mod, or let's do x plus 0. Plus is more benign. Failure. Failure, Will Robinson. Success if there's no bin op inside the if. How crazy is that? That can't be timing at that point, because, oh, I mean, maybe, but this pause is going to, whoops, we left them both active. Okay, wait, that's extra creepy. That's success with both of them. If I take out this one, that's fail. If I take out this one, oh, that's success. So yeah, it's the divide. Dude, this is so weird. Okay, but I think there is an optimization about if statements wrapped with Booleans, right? I don't know why this wouldn't trigger the error, but so there's a thing. So if takes a soft Boolean. So if you say like if x, right? This kind of does a different thing than this, because the equals sign makes it into a Boolean, a real Boolean. Like it knows that the return value is a Boolean. So what if I say Okay, here's the thing. This is why it's not timing. Because we changed x to 1 a while ago, right? So this if will never fire. So we're never doing those pauses and we get a failure, all right? 1,000 pauses should be, let's do a lot of pauses. Okay. This is weird because we should never be doing that. We got a failure. Why? So x is 1, sleep is 2. X is 1. We never increment it. So this is just buggy. I don't understand how we could develop a 100,000 line Sokoban game and have a bug like this. Actually, I do understand because it's computers, right? Oh, right. Sleep is 2. It's integer divide. It's integer divide, right? That's me being tired. Thank you. Thank you. Good point. So it may not be that bad of a bug. Integer divide, bro. You know what that is. So we established this doesn't fail. This doesn't fail. See, that's obviously doing all the pauses and it doesn't fail. Is the timing between this and this really going to be the timing between a success and I just don't believe it. That's why I think it's a bug in the bytecode. It's something about, I'm going to have to look in the next stream. It's something about when there are certain kinds of expressions. And I bet you I have a shortcut of some kind. I bet I have a shortcut. I don't know. I bet I have a shortcut of some kind. I vaguely remember putting something in, and I bet it's wrong. If I do the divide outside the if statement, okay. Div is x divided by sleep, right? Still fails. But if x is equal to 0, that's going to succeed, right? No. So it's just like doing the divide. Oh, div is equal to 0, not x is equal to 0. Getting so confused, man. So if we say if div equals 0, we die. If we don't die. Okay, so the difference between putting an x here and a constant there is whether it's const expr evaluated or not, right? Oh, see, we probably do divided by 1 as a const expr. I don't know if we actually do, but x divided by 2 is a failure, right? So now it's weird. It's a failure whether div is 1 or 0. So, I mean, that's as small of a change as I could tweak it to. So we're completely changing the timing. Now, if I do div equals 1, that's a fail. If I do div, that's a succeed. Whoa, Heisenberg, I guess. So there we have success versus failure, and it's through two things that ought to be the same, right? So this succeeds, this fails. That's not timing. There's no way that that's timing. It's a bug. It's a bug, bro. Did I remember to put in memory barriers? x64 gives you memory sequentiality automatically. Right? So what would I be using a memory barrier for? You can't have non-sequential reads in x64 for all I know. Yeah, so I do have mechanisms to print out the bytecode. I haven't used them in a while. I would probably just factor this into a function that's just this, or just that, and print it out and make sure it's correct. And I bet you it's not. Well, who knows? It could appear correct, and then the actual act of interpretation is incorrect, or whatever. Yeah, here we do not reorder this at all. And in fact, yeah. All right, everybody. That is bedtime for me. We have a very interesting bug to chase down next time. Let's see who's programming. Oh, thank God Pokemon is not yelling at me. All right. Open source programming, Lurk Zone. Animations, will we rage quit Blender? Well, that's not even on. I guess the answer was yes. Elixir parallel locking compiler. That sounds fun. I don't know if the guy will talk. See if you can get this guy to turn his sound on. Or we could do C++. Working on memory profiler. There's not anything happening. And this guy puts his star and his and with the type, which is wrong. So no host. All right. Thanks everybody for coming by. And we're going to host the other dude. And maybe he has a mic. And we'll find out. Thanks. No, it's not the only thing that makes sense. It doesn't make sense.